Long before we learned how to name galaxies or measure the ages of stars, the universe was already quietly arranging itself, not in a rush, not in chaos, simply expanding, layer by layer, following laws older than memory itself. What the James Webb Space Telescope reveals is not a shock, but a kind of gentle reassurance. The universe is not only vast, but more patient than we ever imagined. Distances stretch farther, timelines unfold more slowly, and the earliest galaxies now appear intricate, textured, and quietly alive. In this moment, allow yourself to soften. There is nothing you need to remember, and nothing you need to solve. If this slow unfolding brings you a sense of ease, you are welcome to stay with us by subscribing to the channel, so you can return to this space whenever the world outside feels too loud. Now, as the mind settles and the breath becomes steady, we begin our journey. With no urgency at all, we let the universe reveal its true scale, not as a sudden revelation, but as a flower gently opening, petal by petal, since the very dawn of time. The James Webb Space Telescope exists not merely as a pinnacle of engineering, but as a quiet witness to the unfolding of time itself. To understand why Webb is different, we must first gently change how we think about light. For decades, our picture of the cosmos was shaped by what human eyes could see, extended by instruments such as the Hubble Space Telescope. Hubble, remarkable as it remains, observes primarily invisible light, the same range that colors sunsets and glimmers across the surface of a calm lake. It showed us a universe that was beautiful, structured, and distant. But the universe has a habit of hiding its oldest stories beyond what is easily seen. As light travels across the vast, expanding fabric of space, it slowly stretches. This stretching, known as cosmological redshift, transforms energetic, visible light into longer, quieter wavelengths of infrared. The farther the light travels, the more it changes. By the time it reaches us from the earliest galaxies, it has slipped almost entirely beyond the reach of ordinary vision. Space rarely gives us simple answers, and to reach those first moments of cosmic history, humanity needed a different kind of instrument, one capable of sensing not brightness but warmth, not sharp edges but faint traces. This is what makes Webb truly singular. It does not simply look at the universe, it listens to it. By observing in the near and mid-infrared, Webb is able to peer through thick veils of cosmic dust that once acted like curtains over the birthplaces of stars and galaxies. Where earlier telescopes saw darkness, Webb detects quiet activity. Regions that appeared empty now reveal structure, motion, and life. It is less like a camera and more like a thermal map of creation, translating heat and subtle glow into meaning. We often imagine space as an empty void, but it is anything but empty. It is a crowded tapestry of gas, dust, and faint radiation, layered across enormous distances. Webb's sensitivity allows it to read this layered environment with patience. And because infrared light carries the memory of immense journeys, Webb functions as a genuine time machine. When it observes a distant galaxy, it does not show us how that galaxy looks today. It shows us how it was billions of years ago, when the universe itself was young and still finding its shape. There is also a deeply human story embedded in this mission. Thousands of scientists and engineers spent decades designing a telescope that would never be serviced by human hands. Every fold, every mirror segment, every layer of insulation had to work perfectly the first time. This effort was not driven by urgency or competition, but by endurance and trust. In clean rooms where the mirrors were polished, each hexagonal segment was coated with a layer of gold only a few hundred atoms thick. enough to reflect the faintest infrared light, yet thin enough to remind us how delicate our tools truly are. Numbers whisper more than they speak, and the data now returning is a steady affirmation of those years of quiet dedication. Webb's home is also unlike that of any telescope before it. Positioned far from Earth at a stable gravitational point, it remains in permanent shadow. It must stay cold to hear the universe clearly. Heat, after all, is noise. Silence is also a kind of data. Only in deep cold can Webb sense the faint glow of the earliest stars turning on, ending the long cosmic night known as the Dark Ages. What it gathers is not spectacle, but accumulation. A slow rain of ancient photons, collected patiently over time. As we begin to examine these deep fields, a subtle realization emerges. The early universe was not simple or chaotic. It was already organized, already active, already following patterns we are only beginning to understand. Massive galaxies appear where we expected only diffuse gas. Complexity shows up earlier than predicted. The universe, it seems, knew itself sooner than we assumed. Perhaps the greatest gift Webb offers is not shock, but perspective. It reminds us that darkness is not emptiness, and silence is not absence. Sometimes, what appears quiet is simply waiting for the right way to be heard. For a long time, the earliest chapters of the universe were described using a small number of broad strokes. After the Big Bang, there was light. Then there was darkness. Then, slowly, the first stars appeared and brought the universe into view. This sequence was neat, understandable, and comforting in its simplicity. The period known as the Cosmic Dark Ages was imagined as a long, quiet pause, a time when the universe had expanded enough to cool, but not yet enough to shine. In this picture, darkness meant inactivity. Yet, the universe has always been more subtle than our first descriptions. The afterglow of the Big Bang, the cosmic microwave background, still surrounds us today as a faint, uniform whisper. It tells us that the universe began hot and dense, then expanded and cooled with remarkable regularity. For decades, this background radiation served as our most reliable window into the early cosmos. It showed a universe that was smooth, nearly featureless, with only tiny fluctuations that would one day grow into galaxies. Those small variations were easy to underestimate. Between the fading of that primordial light and the ignition of the first stars lies a span of time we once treated as empty. The Dark Ages were thought to be uneventful, defined more by what was missing than by what was present. No stars, no galaxies, just vast clouds of hydrogen slowly drifting through space. But silence, as we are learning, is also a kind of data. As observations from the James Webb Space Telescope begin to fill in this gap, a different picture emerges. The transition from darkness to light, often called the cosmic dawn, was not a sudden switch being flipped on. It was a gradual, structured process. Even before the first stars fully ignited, matter was already organizing itself. Gravity was quietly at work, pulling gas into filaments, knots, and dense regions long before they became luminous. Space rarely gives us simple answers. What Webb reveals is not a chaotic awakening, but a universe that was already preparing itself. The earliest structures formed earlier and more efficiently than many models predicted. Instead of a long, uneventful night followed by a dramatic sunrise, the universe experienced a slow, layered dawn. Faint sources of light appeared, influenced their surroundings, and reshaped the space around them. Hydrogen was gradually transformed from an opaque fog into a transparent medium, allowing light to travel freely for the first time. This process, known as reionization, was once imagined as a clean milestone. Now it appears uneven, textured, and deeply connected to the environments in which the first stars and galaxies formed. Some regions cleared early, others remained dark much longer. The universe did not awaken all at once. It woke up in pockets, in waves, guided by structure rather than chance. There is something profoundly human in this realization. We tend to imagine beginnings as sudden events, sharp lines between before and after. But in nature, beginnings are often slow, they overlap, they hesitate. The early universe seems to have followed this gentler pattern. Complexity did not arrive late. It was present from the start, waiting for conditions to allow it to show itself. Numbers whisper more than they speak. What feels most unsettling to older models is not that they were wrong, but that they were incomplete. They captured the outline, but missed the texture. Webb does not erase what we knew before. It adds depth. The early universe was never a blank canvas. It was a faintly sketched one, with structure already emerging beneath the surface. As we listen to this deeper story, the universe feels less like a place that stumbled into order and more like one that grew into it naturally. Darkness was not absence. It was incubation. And light did not arrive as a declaration, but as a continuation of processes that had already begun. In the quiet between the first photons and the first stars, the universe was already becoming itself, patiently, without witnesses, waiting for us to learn how to see it. When astronomers first began to map the distant universe, they expected the earliest galaxies to look tentative and unfinished. In the prevailing picture, structure was supposed to emerge slowly. Small clouds of gas would form the first stars. Those stars would gather into modest systems. Over long stretches of time, through mergers and gradual growth, large and organized galaxies would finally appear. Maturity, in this view, was something earned patiently. What recent observations have revealed is quieter but more surprising. As the James Webb Space Telescope peers deeper into cosmic history, it finds galaxies that seem to have skipped several expected steps. These systems appear bright, massive, and well-structured at a time when the universe itself was still young. Some show defined shapes rather than loose, chaotic forms. Others already contain large populations of stars, arranged in ways that suggest stability rather than infancy. Instead of hesitant beginnings, we find confidence. This does not mean that the universe rushed carelessly. It means our intuition about cosmic time has always been shaped by human scales. We are accustomed to slow construction. Cities rise over generations, forests mature over centuries. Even our longest histories feel brief compared to cosmic time. Yet the universe operates on different rhythms. Under the influence of gravity, matter does not always wait. Space rarely gives us simple answers. Among the most striking discoveries are disk-shaped galaxies appearing far earlier than expected. Disk galaxies, like our own Milky Way, are often thought of as the result of long-term settling. Their flattened, rotating structures suggest balance, order, and time. Finding such forms in the early universe challenges the idea that order must come late. Instead, it hints that under the right conditions, structure can emerge efficiently, guided by underlying rules that act quickly and consistently. Some of these galaxies are not only well-shaped but unusually bright. Their light suggests rapid star formation, with stars forming in great numbers over relatively short spans of time. This brightness once led astronomers to believe such objects should not yet exist. They were sometimes described informally as universe breakers, not because they shattered physics, but because they strained our expectations. The universe once again revealed that it does not arrange itself according to our comfort with gradualism. Numbers whisper more than they speak. What these observations suggest is not that our models were wrong, but that they were incomplete. The early universe contained dense regions where gas cooled and collapsed more efficiently than average. In these regions, star formation could accelerate, producing large, luminous systems earlier than anticipated. Webb allows us to see these environments with greater clarity, revealing not isolated anomalies, but patterns that repeat across different regions of space. There is also a human tendency to label anything unexpected as extreme. But from the universe's perspective, these galaxies may not be exceptional at all. They may simply represent what happens when initial conditions align. Gravity does not hesitate. It responds immediately. Where matter is slightly denser, attraction grows stronger, pulling in more material and amplifying small differences into large outcomes. Over cosmic timescales, even a modest head start can lead to rapid maturity. This realization subtly changes how we think about beginnings. We often imagine the early universe as fragile, uncertain, and unfinished. What Webb shows instead is resilience. Even in its youth, the cosmos was capable of building complex systems. The processes that shape galaxies today were already operating, not tentatively, but confidently. Silence is also a kind of data. There is something deeply grounding in this shift of perspective. The universe did not stumble into complexity after ages of trial and error. It unfolded according to rules that were present from the very start. The speed of formation may feel surprising, only because we underestimate how powerful those rules can be when given space and time. For those who study these distant systems, the experience is less about shock and more about recalibration. Expectations are adjusted, assumptions are softened. The universe feels less like a slow machine warming up, and more like a system that was always ready to act once conditions allowed. As we continue to look deeper, these early galaxies remind us that maturity does not always require long delay. Sometimes, given the right balance of conditions, structure emerges quietly and sooner than expected. And perhaps this is one of the most gentle lessons the universe offers. Growth does not always announce itself loudly. Often it has been underway for a long time before we learn how to notice it. In everyday life, distance and time feel like separate ideas. A road stretches away from us, but the present moment remains intact. In the universe, however, distance and time are woven together so tightly that one cannot be sensed without the other. To look far into space is not simply to look outward, it is to look backward into moments that no longer exist except as light still traveling toward us. For generations of astronomers, light has been the universe's most faithful messenger. It carries information across vast distances, revealing where stars shine and galaxies gather. Yet light does not arrive unchanged. As the universe expands, the space between galaxies stretches, and the light moving through that space stretches with it. This gradual elongation shifts light toward longer wavelengths, a process known as redshift. The farther the light has traveled, the more it has been altered, and the deeper into the past it allows us to see. At first, redshift seemed like a technical correction, a mathematical adjustment applied to distant objects, but over time it became something more profound. Redshift turned into a measure of cosmic history. Each increment told a story not only about distance, but about age. When we read redshift, we are reading how long the universe has been expanding since that light began its journey. Numbers whisper more than they speak. This is where the role of the James Webb Space Telescope becomes quietly transformative. Webb does not simply collect faint light. It specializes in light that has been stretched almost beyond recognition. Infrared photons that left their sources billions of years ago arrive at Webb carrying the memory of a universe very different from our own. In this way, Webb functions less like a camera and more like an archive, carefully gathering fragments of a long and unfolding record. When Webb observes a distant galaxy, it is not freezing a moment in time. It is receiving a delayed message. The galaxy we see is no longer there in the same form. Stars may have aged, structures may have changed. Some systems may no longer exist at all. Yet their light continues, steady and patient, crossing expanding space until it finally reaches us. Looking deeper does not bring us closer to the present. It takes us further from it. Space rarely gives us simple answers. What has unsettled earlier expectations is not the existence of this cosmic time delay, but its consequences. The further Webb looks, the more it reveals that early cosmic history was richer than anticipated. Galaxies appear where models predicted only faint beginnings. Structures show complexity where simplicity was assumed. The universe's past, once thought to be sparse and quiet, now appears layered and active. This shift forces us to reconsider how we interpret cosmic timelines. We tend to imagine history as a sequence of clear chapters, one ending before the next begins. The universe does not follow this pattern. Light from different eras arrives together, overlapping in our observations. Webb's deep images are not snapshots of a single moment, but mosaics of many times blended into one view. To read them requires patience and humility. There is a human parallel in this way of seeing. Memory does not work in straight lines either. Our past returns to us unevenly, triggered by fragments, sensations, and echoes. In the same way, the universe offers its history not as a clean narrative, but as a collection of lingering impressions. Webb helps us learn how to listen to those impressions without forcing them into premature conclusions. Silence is also a kind of data. As astronomers interpret these ancient signals, they are learning to slow down. Each faint glow carries uncertainty. Each measurement invites caution. The goal is not to declare final answers, but to let patterns emerge over time. The universe is not in a hurry to explain itself, and neither can we be. Perhaps the most grounding realization is this. When we look far into space, we are not witnessing a distant spectacle unfolding elsewhere. We are engaging with our own origins. The atoms that make up our bodies were shaped by processes whose light is only now reaching us. In reading the universe's deep past, we are also reading a quieter version of our own story. To look outward, then, is to look inward across time. And as the ancient light continues its slow journey toward us, it reminds us that history is never truly gone. It is simply still traveling, waiting to be seen. For many years, supermassive black holes were thought of as the slow results of cosmic patience. In this view, small black holes formed from the collapse of massive stars, then gradually grew larger by pulling in surrounding matter or merging with others. Given enough time, they would eventually become the enormous gravitational centers we observe in mature galaxies today. Size, once again, was assumed to require long duration. What recent observations suggest is something quieter, but far more intriguing. As the James Webb Space Telescope looks deep into the early universe, it encounters black holes that already possess extraordinary mass at a time when the cosmos itself was still young. These objects appear not as tentative beginnings, but as established presences. They are found powering bright early galaxies, shaping their surroundings, and influencing the flow of gas long before such influence was expected. Space rarely gives us simple answers. To understand how this might be possible, astronomers have begun to rethink the earliest stages of black hole growth. One idea involves a process known as super-Eddington accretion. Under normal conditions, as matter falls toward a black hole, the energy released pushes back, limiting how fast the black hole can grow. This balance, once thought to be strict, may be more flexible in the dense environments of the early universe. When gas is abundant and conditions are extreme, black holes may briefly grow faster than previously assumed, quietly accumulating mass without drawing attention to themselves. Numbers whisper more than they speak. Another possibility lies in the way black holes came together in the first place. The early universe was smaller, denser, and more crowded than it is today. In such conditions, black holes would have been closer to one another, increasing the likelihood of early mergers. When two black holes spiral together and combine, they create a single object far more massive than either alone. Over time, repeated mergers could rapidly build the supermassive black holes we now observe at the centers of early galaxies. What is striking is not the violence of these events, but their inevitability. Gravity does not pause to ask permission. Where mass gathers, attraction follows. In the early universe, small imbalances were amplified quickly. Regions with slightly more matter collapsed faster, feeding the growth of both stars and black holes. These ancient gravitational anchors formed early and remained influential ever since. Silence is also a kind of data. Webb's observations allow us to infer the presence of these black holes not by seeing them directly, but by observing their effects. Surrounding gas glows. Galaxies move differently. Light carries subtle signatures of intense gravity at work. In this way, black holes reveal themselves through absence as much as presence. They are known by what they shape rather than what they show. There is a human instinct to associate great influence with long preparation. We expect power to build slowly. Yet the universe often works through quiet efficiency. Under the right conditions, complexity emerges quickly. Black holes did not wait politely for galaxies to mature. In many cases, they appear to have grown alongside them, shaping the flow of matter from the very beginning. This has profound implications for how we understand cosmic structure. Supermassive black holes are not late additions to galaxies. They are foundational elements. Their gravity influences star formation, regulates the movement of gas, and helps define the overall architecture of galaxies. In this sense, these ancient black holes acted as early organizers, guiding the evolution of their environments long before the universe became familiar. There is something grounding in this realization. The universe did not assemble itself randomly and then refine its structure later. Order and influence were present early, embedded within the first systems to form. The cosmos did not wait to become complex. It was capable of complexity almost immediately. For researchers studying these early black holes, the experience is one of adjustment rather than alarm. Models are revised, assumptions are softened. The picture becomes richer, not broken. Webb does not announce a crisis. It offers a deeper view into how efficiently gravity can operate when conditions allow it. As we sit with this understanding, the early universe begins to feel less distant. The forces shaping galaxies today were already active, already steady, already familiar. These ancient black holes remind us that some influences endure across nearly all of cosmic history. And perhaps this is the quiet lesson they offer. What forms early often shapes everything that follows. Long before light filled the universe, gravity was already at work, patient and unyielding, quietly guiding the story toward the structures we now call home. As astronomers began to examine the deepest images returned by the James Webb Space Telescope, they noticed something that did not immediately draw attention through size or brightness. These objects were small, compact, faint, They appeared as tiny red points scattered across the distant universe, easy to overlook at first glance. Yet the more carefully they were studied, the more persistent they became, quietly present, repeated across different observations, refusing to fit neatly into existing categories. They came to be informally known as the little red dots. At first, they did not seem remarkable. Astronomy is full of faint objects at great distances, but these points carried a distinct signature. Their color suggested extreme distance and significant redshift, placing them deep in the early universe. Their compact appearance hinted at dense systems, yet their light didn't behave in ways astronomers expected from known types of early galaxies or active black holes. They were too small for some explanations, too energetic for others. Space rarely gives us simple answers. What makes these objects especially interesting is not that they defy explanation, but that they sit in the spaces between explanations. They do not clearly resemble the star-forming galaxies we recognize, nor do they match the typical signatures of bright quasars powered by supermassive black holes. Instead, they occupy a quiet middle ground, suggesting that the early universe hosted forms of structure we have not yet fully named. Numbers whisper more than they speak. Rather than rushing to label these objects, astronomers have learned to slow down and observe patterns. The little red dots appear consistently across different regions of the sky. They share common properties, hinting that they are not rare accidents, but representatives of a broader population. Their existence suggests that the early universe produced a diversity of systems that our current models did not anticipate. This is not unusual in the history of science. Language often lags behind discovery. We tend to describe new phenomena using familiar terms, stretching old definitions until they no longer quite fit. The little red dots remind us that the universe does not organize itself according to our classification schemes. It creates structures first, names come later. One possibility is that these objects represent an early phase of galaxy formation when stars and central black holes were growing together in tightly bound systems. Another is that they are dominated by accretion processes that look different at high redshift than they do nearby. Or they may be something else entirely, a transitional form that does not persist long enough to be common in the present-day universe. Silence is also a kind of data. What is striking is the restraint with which these discoveries are approached. There is no urgency to resolve every question immediately. Instead, there is careful accumulation, more observations, broader surveys, comparisons across wavelengths. Each piece of data adds a little clarity without forcing a conclusion. The little red dots are allowed to remain partially undefined, and in that uncertainty, they offer valuable information. There is a human resonance here as well. We are most comfortable when the world fits into familiar patterns, but growth often begins at the edges of understanding. New ideas rarely arrive fully formed. They appear first as anomalies, as things that do not quite belong. Only later do they reshape the frameworks that once excluded them. The early universe seems to have followed this same principle. It did not limit itself to a small set of structures. It experimented quietly and efficiently, producing systems that served their purpose for a time and then faded. Some became the ancestors of modern galaxies. Others may have existed only briefly, leaving behind faint traces for instruments like Webb to uncover. As we continue to study these small red points, they encourage a gentle humility. The universe contains more variety than our current language can capture. Our models are maps, not the territory itself. They guide us, but they do not define reality. In the end, the little red dots are not a problem to be solved, but a reminder to be attentive. They suggest that the early cosmos was not only active, but inventive. And as we learn to observe more carefully, we may find that the universe has been speaking in many dialects all along, waiting for us to listen long enough to hear them. For much of modern astronomy, the universe was imagined as a vast stage dotted with individual actors. Stars formed galaxies. Galaxies gathered into clusters. Between them stretched enormous regions that seemed largely empty. Distance and size dominated our thinking. The universe felt immense because its objects were far apart, separated by darkness that appeared passive and still. Yet this picture was always incomplete. As observations deepened and simulations improved, a quieter structure began to reveal itself. Galaxies were not scattered randomly. They followed patterns. They traced invisible pathways, forming filaments and intersections that stretched across cosmic scales. What emerged was not a collection of points, but a network. A vast interconnected architecture now known as the cosmic web. Space rarely gives us simple answers. The cosmic web is shaped by gravity acting over immense spans of time. In the earliest moments after the universe cooled enough for matter to move freely, tiny differences in density began to matter. Regions that were slightly denser than their surroundings pulled in more material. Over time, these small imbalances grew, stretching into elongated filaments and dense nodes. Galaxies formed along these filaments, while clusters arose at their intersections. What we once perceived as emptiness was, in fact, structure too faint to see with earlier tools. At the heart of this web lies something we cannot observe directly. Dark matter does not emit light or heat, yet it outweighs ordinary matter by a wide margin. Its presence is inferred through motion, through the way galaxies orbit one another, and through how light bends as it travels across space. Dark matter acts as the scaffolding of the universe. Ordinary matter settles into its gravitational framework, lighting up the invisible architecture with stars and galaxies. Silence is also a kind of data. What makes this realization especially powerful is that it shifts our sense of scale. The universe is not defined only by how large it is, but by how it is connected. Two galaxies separated by millions of light years may still be part of the same filament, shaped by the same underlying gravitational flow. Their histories are linked, even if they never meet. The true size of the universe, in this sense, is measured not just in distance, but in relationship. The James Webb Space Telescope plays a subtle role in bringing this structure into clearer focus. While it does not see dark matter directly, its ability to observe faint galaxies at great distances allows astronomers to trace where matter has gathered over time. By mapping the distribution of early galaxies, Webb helps confirm that the cosmic web was already forming when the universe was young. The large-scale structure we observe today did not arise suddenly. It was woven gradually, thread by thread, guided by forces that remain steady and patient. Numbers whisper more than they speak. There is a human analogy that resonates here. We often think of ourselves as individuals moving independently through the world, yet our lives are shaped by networks we rarely see. Families, cultures, ecosystems, and histories connect us in ways that extend far beyond immediate experience. The cosmic web mirrors this truth on a grand scale. No galaxy exists in isolation. Each is part of a larger pattern, influenced by flows of matter and gravity that stretch across the universe. Understanding the cosmic web also changes how we interpret motion. Galaxies are not simply drifting through empty space. They are moving along pathways shaped by gravitational currents. Gas flows into galaxies along filaments, fueling star formation. Clusters grow by drawing in material from surrounding strands. the universe behaves less like a static arrangement and more like a slow, continuous circulation. This perspective helps explain why some regions of space are rich with galaxies while others appear sparse. Voids are not failures of formation. They are natural outcomes of matter flowing elsewhere. Emptiness, in this sense, is not absence but redistribution. What seems missing in one place has gathered in another. For scientists, mapping this vast network requires patience. The signals are faint. The patterns emerge only when many observations are combined. No single image reveals the cosmic web in full. It is seen gradually through careful comparison and long-term study. This process mirrors the structure itself. Connection becomes visible only over time. There is a quiet comfort in this view of the universe. It suggests coherence rather than randomness, complexity rather than chaos. The cosmos is not a scattering of unrelated parts. It is an integrated whole, shaped by simple rules applied consistently across immense scales. As we reflect on this hidden network, the universe feels less distant and more intimate. Its true scale is not just the span between galaxies, but the threads that bind them together. And as we continue to trace those threads, we are reminded that meaning often resides not in isolated objects, but in the connections that quietly hold everything in place. Between the stars, the universe appears calm and empty at first glance. Vast distances separate points of light, and the darkness between them feels still, almost untouched. For a long time, this space was treated as little more than a backdrop, a quiet gap through which stars and galaxies simply happen to move. Yet the universe has always been more intricate than its silhouettes suggest. The space between stars is known as the interstellar medium. It is composed of gas, dust, faint radiation, and magnetic fields, spread thinly across enormous volumes. Though its density is low by earthly standards, its influence is profound. This material is the reservoir from which stars are born, and the archive that preserves the traces of events long past. The interstellar medium is not emptiness, it is context. Space rarely gives us simple answers. Within this diffuse environment, light does not travel freely and forgetfully. When a bright event occurs, such as the ignition of a massive star or the explosive end of one, its light spreads outward in all directions. Some of that light travels directly to us. Other portions encounter clouds of dust along the way. When light reflects off these distant grains, it arrives delayed, scattered, and softened. This phenomenon is known as a light echo. A light echo is not a repetition of the original event, but a memory of it. It allows astronomers to observe past moments long after they have faded, sometimes from entirely new angles. In effect, the interstellar medium acts as a natural recording system. Dust grains become quiet witnesses, redirecting ancient light so that it reaches us years, decades, or even centuries later. Time, once again, becomes layered. Silence is also a kind of data. These echoes reveal more than the events themselves. They trace the structure of the space between stars. By studying how light is scattered and delayed, astronomers can map the distribution of dust and gas that would otherwise remain invisible. The interstellar medium takes shape not through brightness, but through subtle interaction. Its presence is known by how it alters what passes through it. The James Webb Space Telescope has expanded our ability to study this quiet environment. With its sensitivity to infrared light, Webb can detect the faint warmth of dust clouds and the gentle glow of gas that older instruments could not resolve. It does not isolate stars from their surroundings. It shows them embedded within complex environments, shaped by what lies between them as much as by what burns at their cores. Numbers whisper more than they speak. What emerges from these observations is a sense of continuity. Stars are not isolated points of creation. They are part of an ongoing exchange. They form from interstellar material, influence it through radiation and winds, and eventually return matter back to it when they die. The interstellar medium is both origin and destination. It carries the chemical memory of generations of stars, enriching future systems with heavier elements and more complex structures. There is a human resonance in this idea. We often think of history as something that happens only at the surface, invisible events and decisive moments. But much of what shapes us happens quietly, in the spaces between. Context matters, environment matters. The interstellar medium reminds us that influence does not require density or force. Even the faintest material, spread thinly enough, can guide the evolution of entire systems. Light echoes reinforce this lesson. They show us that the past does not disappear when an event ends. It continues to travel, reflect, and resurface, shaped by the environment it encounters. The universe remembers itself not through intention, but through interaction. As astronomers continue to study these faint signals, they are learning to pay attention to what was once dismissed as background. The spaces between stars are not passive voids. They are active participants in cosmic history, carrying structure, memory, and possibility across time. In this softly illuminated network of gas and dust, the universe reveals one of its quieter truths. What lies between things often matters as much as the things themselves. And in the gentle echoes of ancient light, we are reminded that nothing in the cosmos exists alone, not even the darkness. After the universe cooled enough for atoms to form, space entered a long, quiet interval. Matter spread thinly. Light faded into the background. Hydrogen filled the cosmos in a neutral state, absorbing radiation and limiting how far light could travel. This period is often described as dark, but not because nothing was happening. It was dark because the universe had not yet learned how to shine. The first stars marked a turning point. These earlier stars, often referred to as population 3, were unlike any stars we see today. They formed from pristine material, composed almost entirely of hydrogen and helium, untouched by earlier generations. Without heavier elements to regulate their growth, these stars likely became massive very quickly. They burned hot and bright, living short lives by stellar standards. Their existence was brief, but their influence was enduring. Space rarely gives us simple answers. As these first stars ignited, they began to release intense ultraviolet radiation. This light did not merely illuminate their immediate surroundings. It transformed the space between galaxies. Neutral hydrogen, once opaque to light, was gradually stripped of its electrons. This process, known as reionization, changed the universe from a foggy, light-blocking medium into a transparent one. Once this transformation progressed far enough, light could travel freely across vast distances for the first time. Reionization was not a single moment. It was a gradual, uneven process. Some regions cleared early, lit by clusters of young stars and growing galaxies. Other areas remained neutral for much longer. The universe brightened in patches, slowly knitting together into a more transparent whole. What we experience today as an open, visible cosmos emerged through this patient unfolding. Silence is also a kind of data. For many years, models suggested that this transition would take considerable time, driven by small numbers of early stars. Yet observations now suggest that the early universe may have brightened more efficiently than expected. There appears to have been more light earlier than intuition once allowed. This does not imply excess or disorder. It suggests that the first sources of light were effective at shaping their environment, working collectively rather than in isolation. The James Webb Space Telescope has become an essential tool in exploring this era. By detecting faint galaxies at extreme distances, Webb allows astronomers to estimate how much light early systems produced and how it interacted with surrounding gas. It does not observe the first stars directly, but it traces their influence through the conditions they left behind. The clarity of distant space itself becomes evidence of their presence. Numbers whisper more than they speak. Rionization represents more than a technical phase change. It is a reminder that light reshapes space as much as it reveals it. The first stars did not simply appear within the universe. They altered its fundamental character. By changing how matter interacted with radiation, they opened the cosmos to observation, allowing later generations of stars, galaxies, and eventually observers to see across time. There is something deeply human in this story. We often think of beginnings as small and tentative. Yet the first stars demonstrate that beginnings can be decisive. Their light carried energy, structure, and consequence far beyond their brief lives. They did not persist, but the transparency they created endured. As astronomers reconstruct this period, they do so carefully. The signals are faint. The conclusions are probabilistic. No single observation defines the full picture. Instead, understanding emerges through convergence as independent lines of evidence align. The universe reveals its past slowly, inviting patience rather than certainty. In the end, reionization is a story about connection. Light linked distant regions. Space became shared rather than isolated. What was once fragmented became continuous. The universe learned how to let light travel, and in doing so, it became a place where history could be seen. As we reflect on this transformation, the early cosmos no longer feels distant or abstract. It feels formative. In the quiet glow of the first stars, space itself was changed, not suddenly, but permanently. And in that gentle transition from darkness to clarity, we find a reminder that even the faintest light, when sustained, can reshape everything around it. The early universe is often imagined as a place of gentle beginnings, where light slowly emerged from darkness and structure formed with careful restraint. Yet beneath this calm progression lay moments of intense activity. The young cosmos was not silent. It carried episodes of sudden release, brief but influential, shaping its evolution in ways that reached far beyond their immediate surroundings. Among the most important of these events were supernovae. When the most massive stars reached the end of their short lives, they did not fade quietly. Their cores collapsed, and in the process, vast amounts of energy were released into surrounding space. These explosions scattered newly forged elements outward, enriching the environment and altering the conditions for future star formation. Even in the universe's earliest eras, death was a source of creation. Space rarely gives us simple answers. In regions where stars formed rapidly and densely, these explosions were not isolated occurrences. They unfolded within extreme environments, where massive stars were born in close proximity and lived briefly before ending their lives almost together. The collective influence of their supernovae reshaped nearby gas clouds, compressing some regions while dispersing others. Star formation was not a steady, uniform process. It pulsed, responding to cycles of collapse and disruption. Alongside supernovae, the early universe also hosted gamma-ray bursts. These events are among the most energetic phenomena known, releasing focused beams of radiation that can travel across immense distances. Though brief, they carry immense power, marking the collapse of particularly massive stars or the merger of compact remnants. In the early cosmos, such events were more common than they are today, simply because massive stars were more abundant. Numbers whisper more than they speak. What makes these high-energy events especially important is not their drama, but their consequence. Gamma-ray bursts and supernovae altered their surroundings profoundly. They heated gas, drove chemical change, and influenced how matter gathered afterward. In this way, even brief flashes played a role in shaping long-term structure. The universe did not grow only through gradual accumulation. It was also sculpted by interruption. The James Webb Space Telescope allows astronomers to study the environments where these events occurred, even if the explosions themselves are long past. By examining the chemical fingerprints left behind, Webb reveals regions that were enriched early, suggesting prior generations of massive stars and energetic endings. The presence of heavier elements in young galaxies tells a story of cycles already underway. Silence is also a kind of data. There is a human tendency to associate quietness with simplicity. Yet the early universe challenges this assumption. Even when light was sparse, processes were active. Energy was released, matter was transformed, and environments evolved rapidly. The calm appearance of distant space today does not reflect the intensity of its youth. Understanding these events also reshapes our view of balance. Supernovae and gamma-ray bursts were not disruptions that hindered formation. They were integral to it. By redistributing material and injecting energy, they prevented gas from collapsing too uniformly. They created diversity. They ensured that star formation occurred in varied and dynamic ways. This balance between violence and order is not unique to cosmology. In many natural systems, growth depends on disturbance. Forests renew after fires. Ecosystems diversify through change. The universe, it seems, follows a similar principle. Stability emerges not in the absence of energy, but through its careful redistribution. As we reflect on the early cosmos, we are invited to let go of the idea that quietness means inactivity. The young universe was filled with brief, powerful moments that shaped everything that followed. These events did not dominate the sky forever. They passed, but their influence endured, written into the structure and composition of galaxies. In the end, the early universe reveals a gentle truth. Even in its most energetic moments, it was not chaotic. It was purposeful, responsive, and balanced. And as we listen carefully to its faint signals today, we learn that what once seemed violent was, in fact, part of a larger harmony that continues to unfold. There are moments in astronomy when distance does not behave the way intuition expects. We imagine that to see farther, we must build larger instruments or move closer to what we wish to observe. Yet the universe has quietly provided its own solution. It bends space itself, turning gravity into a natural lens that allows distant light to be stretched, curved, and magnified along its journey toward us. This phenomenon is known as gravitational lensing. According to our best understanding of gravity, massive objects do not simply sit within space. They shape it. Galaxies, clusters of galaxies, and vast concentrations of matter gently curve the space around them. When light from a far more distant object passes through this curved region, its path is altered. The light does not slow down or stop. It follows the geometry of space itself, arriving at our instruments brighter, distorted, and sometimes multiplied. Space rarely gives us simple answers. Gravitational lensing does not create new light. It reshapes existing light, revealing sources that would otherwise remain beyond reach. In some cases, A single, distant galaxy may appear stretched into arcs. In others, it may be duplicated into multiple images, each arriving along a slightly different path through space. Time itself becomes layered, as light traveling along longer routes arrives moments later than light that followed a shorter curve. This quiet bending of space has become one of the most valuable tools in modern astronomy. It allows us to observe galaxies that formed in the early universe without physically traveling closer to them. The universe acts as its own magnifying glass, extending our vision naturally, patiently, and without effort on our part. Numbers whisper more than they speak. Deep field observations take full advantage of this effect. When telescopes focus on small, seemingly empty regions of sky for extended periods, they collect faint light that accumulates slowly over time. In regions where gravitational lensing is present, these deep fields become even more powerful. Light from the most distant galaxies is amplified, allowing astronomers to study objects that would otherwise be too faint to detect. The James Webb Space Telescope has refined this approach with remarkable sensitivity. Webb's ability to observe faint infrared light pairs naturally with gravitational lensing. Together, they extend our reach without increasing complexity. Webb does not need to push harder or look faster. It simply listens longer, allowing space itself to assist in the act of observation. Silence is also a kind of data. Gravitational lensing reveals more than distant galaxies. It maps invisible structure. The degree of bending depends on how much mass lies between us and the source. By studying the distortion of background light, astronomers can infer the distribution of matter, including dark matter, even when it emits no light of its own. In this way, lensing becomes a way of seeing the unseen, tracing the quiet architecture of the universe. There is something deeply elegant in this process. The universe does not resist observation. It participates in it. Space curves, light adapts, and information flows outward across billions of years. Distance becomes less of a barrier and more of a feature, shaping what we see rather than blocking it. There is also a human lesson embedded here. We often assume that progress requires force, speed, or proximity. Yet, gravitational lensing demonstrates that clarity can arise from patience and alignment. When conditions are right, insight emerges naturally. No intervention is needed beyond careful attention. As astronomers interpret lensed images, they do so with restraint. Distortions must be understood, not corrected away too quickly. The warped shapes carry information. They speak of mass, distance, and time all at once. The image is not flawed. It is expressive. In this way, the universe reveals one of its quieter strategies. It allows its own structure to extend our vision. We do not see deeper by crossing space. We see deeper because space itself cooperates. And as we let these bent paths of light guide us, we are reminded that perspective matters as much as distance. Sometimes, the deepest views come not from moving closer, but from learning how to look through the curves already present in the fabric of the cosmos. When we speak about the size of the universe, we often imagine a boundary waiting to be reached, a distant edge, a final wall of stars. Yet the universe does not present itself that way. What we can see is not defined by how far space extends, but by how far information has had time to travel. The observable universe is not the whole of existence. It is the portion of reality that has had enough time to make itself known to us through light. This distinction matters. The observable universe is shaped by time as much as by distance. Light moves at a finite speed. Even though the universe is vast, only light that has had enough time to reach us since the beginning can be observed. Everything beyond that horizon may exist, but it remains causally disconnected from us for now. not hidden by technology, not obscured by darkness, simply separated by the structure of space and time itself. Space rarely gives us simple answers. As the universe expands, this horizon does not behave in intuitive ways. Some regions move away from us faster than light can bridge the gap, not because they are traveling through space too quickly, but because space itself is expanding between us. This means that certain parts of the universe, even if they emit light today, will never be able to send that light to us. Their signals are stretched, diluted, and ultimately carried beyond reach by the expanding fabric of space. This is not a failure of observation, it is a feature of the universe. The James Webb Space Telescope extends our vision deeper than any previous instrument, but it does not remove these fundamental limits. Webb can detect fainter light, observe longer wavelengths, and study earlier cosmic eras with greater clarity. Yet even Webb observes within the same cosmic boundary. It cannot see beyond the observable universe because there is no information arriving from beyond it. Numbers whisper more than they speak. This realization invites a quieter form of understanding. Progress in astronomy is often imagined as a steady march towards seeing everything. But some limits are not meant to be crossed. They are woven into the universe itself. No matter how refined our instruments become, there will always be regions whose light has not yet reached us, and others whose light never will. There is something deeply stabilizing in this idea. It suggests that mystery is not merely a temporary inconvenience, it is a permanent companion. The universe is not withholding information out of indifference. It is structured in such a way that not all knowledge can be immediate or complete. Silence is also a kind of data. The absence of signals beyond the cosmic horizon tells us something important. It defines the shape of causality. It sets the scale of what can influence us and what cannot. Within the observable universe, events can shape one another over time. Beyond it, they remain independent, unfolding without interaction. This boundary gives meaning to the idea of a shared cosmic history. For scientists, working within these limits requires humility. Models are constructed knowing they describe only a portion of what exists. Measurements are interpreted with the understanding that they apply locally, not universally. The observable universe becomes a laboratory defined not by walls but by time. There is a human parallel here as well. Our lives are shaped by horizons of experience. There are events we can remember and others that lie beyond memory. There are futures we can imagine and others that remain unknowable. These limits do not diminish meaning. They give it form. As Webb continues to observe the earliest galaxies and faintest structures within reach, it does so at the edge of what can be known, not because of technological restraint, but because of cosmic design. The universe invites exploration, but it does not promise completeness. In this way, the observable universe teaches a gentle lesson. Knowledge grows not by eliminating boundaries, but by understanding them. The limits we encounter are not obstacles to be overcome. They are features to be respected. And perhaps this is one of the quiet comforts of cosmology. We do not need to see everything for the universe to be whole. We only need to listen carefully to what reaches us, trusting that what lies beyond continues its own story, unfolding patiently, whether we are there to observe it or not. When astronomers measure the universe, they are not simply recording distances. They are listening for rhythm. Expansion is not something we see directly. It is something we infer from patterns in light, from the way galaxies drift apart, and from how ancient signals reach us across time. For much of the last century, these measurements told a consistent story. The universe is expanding, and it does so at a measurable rate. Yet as our tools have grown more precise, a quiet discrepancy has emerged. Different methods of measuring the expansion of the universe do not quite agree. Observations based on the early universe, using relic radiation from the Big Bang, suggest one rate. Measurements taken from the nearby universe, using stars and galaxies whose distances can be determined more directly, suggest another. This difference is known as the Hubble tension. It is not a dramatic conflict. It is a subtle mismatch, small in scale, but persistent. Space rarely gives us simple answers. At its heart, the Hubble tension is a conversation between methods rather than a failure of measurement. Each approach is reliable within its own context. One looks far back in time, capturing the universe as it was shortly after its beginning. The other looks closer, measuring how space behaves in the present. Both are carefully calibrated. Both are internally consistent. And yet, they tell slightly different stories. Numbers whisper more than they speak. This situation invites patience rather than alarm. The universe has not changed its behavior unexpectedly. Instead, we may be learning that its expansion has more nuance than a single number can express. The difference between these measurements could reflect new physics, subtle effects of cosmic structure, or simply aspects of the universe we have not yet fully accounted for. The James Webb Space Telescope contributes to this conversation not by resolving the tension outright, but by refining the data on which these measurements depend. Webb observes distant galaxies and stellar populations with greater clarity, helping astronomers calibrate cosmic distances more accurately. It improves the foundations of our measurements, even if it does not yet deliver a final answer. Silence is also a kind of data. In science, unresolved questions are not signs of weakness. They are signs of growth. The Hubble tension does not suggest that cosmology is broken. It suggests that our understanding is still incomplete. History shows that many advances begin as small inconsistencies, noticed only because measurements become precise enough to reveal them. There is also a human dimension to this story. We often expect agreement to mean correctness and disagreement to mean error. But in complex systems, multiple perspectives can coexist, each capturing a different aspect of reality. The universe may not expand at a single, simple rate across all eras and environments. Its behavior could depend on time, scale, or conditions we are only beginning to explore. This realization encourages a softer relationship with uncertainty. Rather than rushing to resolve the tension, scientists are allowing it to guide new questions. What assumptions underlie each measurement? What processes might influence expansion differently in the early and late universe? How local structure could subtly affect what we observe nearby. As these questions are examined, the universe remains steady. Galaxies continue to drift apart. Light continues to travel. The discrepancy does not disrupt the cosmos. It simply invites deeper listening. In the end, the Hubble tension reminds us that measurement is a dialogue, not a verdict. Each method speaks with its own voice, shaped by what it observes and how it observes it. When those voices differ, the task is not to silence one, but to understand the harmony they are pointing toward. And as we hold this quiet disagreement without urgency, we are reminded that knowledge often advances not through certainty, but through careful attention to what does not yet align. When we look at the night sky, nearly everything we see is made of a small fraction of what the universe contains. Stars, planets, gas, and dust feel tangible because they emit or reflect light. Yet these familiar forms account for only a minor portion of cosmic reality. The larger part remains unseen, influencing the universe not through brightness but through gravity and expansion. It is this invisible majority that quietly governs the universe's past, present, and possible futures. Dark matter is the first of these unseen components. It does not glow, absorb light, or reveal itself directly. Its presence is inferred through motion. Galaxies rotate faster than visible matter alone can explain. Clusters of galaxies remain bound when their luminous contents should drift apart. Light bends more strongly than expected as it passes through empty-looking regions. In each case, something unseen is shaping the outcome. Dark matter acts as the hidden framework of the universe, guiding how ordinary matter gathers and moves. Space rarely gives us simple answers. Dark matter does not form stars or planets. It does not clump into visible structures. Instead, it forms extended halos around galaxies and filaments across cosmic scales. Ordinary matter settles into these gravitational contours, lighting them up with stars and gas. Without dark matter, galaxies as we know them would not exist. It is not an accessory to cosmic structure. It is its foundation. Dark energy is more elusive still. While dark matter pulls inward through gravity, dark energy pushes outward, driving the accelerated expansion of the universe. Discovered through careful observations of distant galaxies, it reveals itself not by attraction, but by absence. Space itself appears to be gaining energy, causing galaxies to drift apart faster over time. This expansion is not slowing, it is gently increasing. Numbers whisper more than they speak. Together, dark matter and dark energy form the backbone of the standard cosmological framework, often called the Lambda-CDM model. This model has been remarkably successful in describing large-scale structure, cosmic background radiation, and the growth of galaxies. Yet it rests on components we do not fully understand. We can measure their effects with great precision, while their true nature remains unknown. This tension is not a failure, it is a reminder of scale. The James Webb Space Telescope does not detect dark matter or dark energy directly. What it does is refine the visible story that surrounds them. By observing early galaxies, tracing structure formation, and improving distance measurements, Webb helps constrain how these invisible components must behave. Each new observation narrows the range of possibilities without forcing premature conclusions. Silence is also a kind of data. The future of the universe is shaped largely by the balance between these unseen forces. If dark energy remains steady, the universe will continue to expand, with galaxies slowly drifting beyond one another's reach. If it changes over time, other outcomes become possible. Expansion could slow, accelerate further, or evolve in unexpected ways. The universe's fate is not written in spectacle, but in subtle trends unfolding across billions of years. There is something quietly humbling in this realization. The destiny of everything we know depends on components we cannot see and forces we can only infer. Yet this invisibility does not imply fragility. The universe has been governed by these forces since its earliest moments, maintaining coherence and structure across unimaginable scales. There is also a human echo here. Much of what shapes our lives remains unseen. Context, history, and underlying conditions influence outcomes more than visible events alone. Dark matter and dark energy remind us that influence does not require presence in the spotlight. As cosmologists explore possible refinements to existing models, they do so carefully. Tensions are examined, assumptions are tested. New ideas are introduced gently, not to replace what works, but to understand it more fully. The goal is not to dismantle the current picture, but to deepen it. In the end, dark matter and dark energy invite a particular kind of patience. They suggest that understanding does not always arrive as revelation. Sometimes it arrives as accommodation, as the slow acceptance that the universe operates with ingredients beyond immediate perception. And as we contemplate this open future, one truth becomes clear. The universe is not driven by what shines, but by what persists. Its fate unfolds quietly, shaped by forces that neither announce themselves nor hurry. In learning to listen to these unseen influences, we are reminded that the deepest structures often work without display, guiding everything forward in calm and steady ways. As our understanding of the universe grows, it is easy to assume that expansion brings unease, bigger distances, longer timelines, forces beyond direct control. Yet the deeper lesson of modern cosmology is not one of fear, but of steadiness. The universe does not reveal its scale to diminish us. It reveals it to place us more gently within a larger whole. For centuries, science has often been associated with acceleration, faster travel, quicker communication, more immediate answers. But astronomy offers a different rhythm. It asks us to wait, to listen, to accept that some truths unfold only across vast spans of time. In this way, cosmic knowledge does not sharpen urgency, it softens it. Space rarely gives us simple answers. When we encounter the immensity of the cosmos, the first response can feel like smallness. Our planet is one world among countless others. Our lifetime is brief compared to stellar ages. Yet this perspective changes when we look more carefully. The universe is not composed of anonymous points. It is structured, connected, and shaped by the same principles everywhere. To exist within it is not to be insignificant. It is to participate in something coherent. Understanding scale alters how we experience time. When we learn that light can travel for billions of years before reaching us, our own pace begins to feel different. Daily concerns lose some of their urgency. Long-term patterns become more visible. The universe invites us to think in terms of processes rather than moments, continuity rather than events. Numbers whisper more than they speak. There is also a human comfort in knowing that the universe does not demand our constant attention. Stars form and fade without our intervention. Galaxies evolve independently of our concerns. This separation can feel liberating. It allows us to step back from the idea that everything must be managed, controlled, or resolved immediately. The cosmos continues whether we watch it or not. At the same time, our ability to understand the universe connects us to it. Through observation and reasoning, we become part of its self-awareness. Instruments like the James Webb Space Telescope extend our senses, allowing us to perceive patterns far beyond our natural limits. This is not dominance, it is participation. We do not command the universe, we learn from it. Silence is also a kind of data. Science, at its best, teaches humility without erasing meaning. It reminds us that not knowing everything is not a flaw. It is a condition of being human. The universe is not a puzzle designed for quick completion. It is an environment to be explored gradually, with care and respect for its complexity. When we place ourselves within this broader picture, our sense of purpose shifts. Meaning no longer depends on scale or permanence. It emerges from relation, from understanding how small systems fit within larger ones, from recognizing that influence does not require size, and presence does not require permanence. There is a quiet dignity in this perspective. Our lives are brief, but they are real. Our actions are local, but they matter. The universe does not erase significance by being large. It reframes it. As knowledge grows, fear often recedes. Uncertainty becomes less threatening when it is understood as natural. The vastness of space no longer feels like emptiness, but like context, a backdrop that holds our stories without overshadowing them. In this way, cosmology offers a kind of rest. It does not push us toward conclusions. It invites reflection. It allows us to release the need for constant answers and settle into curiosity instead. As we reach the end of this journey through scale, structure, and time, there is no final revelation waiting, only a sense of alignment. The universe continues to unfold, and we continue to observe, learn, and adapt. And perhaps this is the most enduring lesson of all. To understand the universe is not to shrink within it, but to slow down enough to feel at home in its vast, patient rhythm. As this quiet journey comes to a close, nothing in the universe has reached an ending. Galaxies continue to drift. Light continues to travel. The structures we have explored remain in motion, following patterns far older than any single observer. What changes gently is our relationship to what we have heard. The universe revealed through careful observation is not louder than before. It is calmer. Its vastness does not press in on us. It opens outward, offering space rather than demand. When we learn how large the cosmos truly is, we are not asked to feel overwhelmed. We are invited to breathe more slowly. There is comfort in knowing that the universe does not hurry. Stars form on timescales beyond impatience. Galaxies evolve without urgency. Even the most energetic events pass, leaving behind structure and balance. Against this backdrop, our own moments gain a quieter clarity. Not everything must be solved tonight. Not everything needs an answer. Silence is also a kind of data. In the end, science does not remove mystery. It reshapes it into something gentler. The unknown becomes a companion rather than a threat. The limits of what we can see are not failures, but boundaries that give meaning to what is within reach. As you rest now, remember that you are part of this unfolding story. The atoms that make you were shaped by ancient stars. The light you have imagined tonight began its journey long before memory. You are not separate from the universe you observe. You are one of its quiet expressions. If sleep comes, let it come naturally. If thoughts linger, let them drift without direction. The universe will continue whether you watch or not, steady and patient. And when you return to the night sky another time, it will be there, not waiting, not changing its pace, simply existing, offering perspective without asking anything in return. For now, there is nothing more you need to do. Just rest within the vastness, knowing that understanding does not require effort, only attention.